Okay, everyone, welcome to this talk. Today we have Hoang Nguyen from Coventry University. Dr. Nguyen is the Associate Professor in Automotive Cybersecurity at its Research Institute for Clean Growth and Future Mobility. His current research agenda includes cybersecurity in automotive and autonomous systems. His recent work focuses on automotive threat modeling, risk assessment, security solutions, and security testbed. Today, he's going to talk about a real-time automotive testbed for developing and validating security solutions. Now I pass the stage to Dr. Nguyen.
Thank you very much, Changu. Hello, everyone, and welcome to my presentation. So my name, as introduced, Hoang Nguyen. I'm an associate professor at Coventry University. So I actually come from system security groups from something we call Center for Future Transport and City. It's a center inside the Research Institute. I'm honored to be here today present our recent work to all of you. Although we already know that in the automotive industry, testbed has been widely used for testing functionalities as well as safety, but we actually developed a novel automotive testbed specifically for developing and validating security solutions. I would like to send my thanks to my colleagues, so Hesam and Jiras, for their contribution to this work. Before I actually started my presentation, I would like to do an advertisement for two opening positions at our group. So we have an assistant professor in system security and also a position associate professor in system security. And if you want to know more detail about these two positions, please following the links on the screen. And the deadline for both of them would be the 21st of November 2021. That's my thank you. Okay, so in this presentation, I would like to do three things. First, I would try to explain why we need such a testbed. In particular, I give the current pictures of the automotive cybersecurity, then how solution has been developed for the domain, and finally, what are the existing testbed and why they are not, good enough for us. The second thing I want to do is explain how we design and build our testbed. Finally, I will demonstrate our testbed, through two examples. In the first example, we use this testbed to develop and validate an intrusion detection system based on one class support vector machine. The second example is the use of this testbed to validate a system on chip monitoring solution from one of our industrial partners. Okay, so let me start with this picture, which probably many of you would be familiar with. So nowadays, it is common practice that each car is embedded with maybe about 100 microcomputers called ECUs. They control different physical parts of the cars. There are ECUs that dealing with the powertrain, like transmissions and engine. Others are responsible for infotainment features such as audio, video, and navigation. They are connected by in-vehicle networks, which is in cybersecurity term, it provides an environment for cyber attack to happen. Okay, obviously the picture doesn't stop there. So to make things even worse, today's cars also are usually equipped with ECU such as the head unit and telematics, which has the capability to connect to the outside world via GPS, mobile network, Wi-Fi, Bluetooth, and different kind of short-range radios. This kind of pictures also give cyber attacker even more attack vectors to penetrate and compromise the weaker systems and subsystem and eventually cause damage. And why is this the case? So in this talk, I actually try to focus on the in-vehicle networks, which usually happen here is the CAN burst network. And the CAN burst actually expose a number of vulnerabilities. I would try to give some examples of the cyber attacks that happen on cars shortly. For the scope of this presentation, as I said, I would focus on CAN burst, which is mostly used in network. They has been invented for a long time now, and because of this legacy, this kind of network expose a lot of vulnerabilities. The first one is that the nature of the broadcast transmissions in the network. This means that any ECU can send message, and which would be received by all other ECUs. Secondly, there is no authentication or encryption supported by the network. So this, what does this mean? This means that when you receive a message, you cannot validate whether it actually came from the ECU that you want it to come from, and all the message would be exposed to any attacker, in terms of plain text. The reason for this is that this kind of network is built to satisfy real-time requirement. For example, when you press the gas pedal or the brake pedal of your car, you want the command control from this action to be responsive as soon as possible. So you don't want any delay in there. Finally, the message, the mechanism of sending the message also based on priority. So when two ECUs send message at the same time, then based on the ID of each message, it would determine which ECUs, which message would be sent over the other. Also, it means that if an ECU is compromised, it can send the message to prevent other messages, to prevent other ECUs sending the message by broadcasting the highest priority message. So this means that no one can send any message. Okay, so we know this kind of vulnerabilities for the CAN burst, and then I want to talk about 3 examples of attacks that already happened. I don't have time to go over all of the cyber incident, but I'll try to pick the 3 most notorious ones. The first example was reported actually about nearly 20 years ago, where car enthusiasts were able to modify ECUs. The purpose was to increase the car performance by identifying and isolating the right ECUs, the right engine ECU, free flashes, so that it could change the control of the engine, usually provide more gas or air to the engine so that the power of the engines increase. This hack obviously violates the integrity of the ECUs. If someone can change the control command inside ECUs, and they can also do it in a bad way so that maybe the car would run into trouble. I think the next example is probably a famous one. This is a more recent one performed by 2 researchers named Miller and Valencia. They can compromise the Uconnect head unit from a Cherokee wirelessly via the mobile connections. This allows them to take control of the car, such as so that it would lead to dangerous situations. For example, like they can disabling the braking system. So imagine that you go on the motorway and then your brake doesn't work anymore. How frustrating, how scary it could be for you. Eventually, Fiat Chrysler has to make an expensive recall to fix the problem to all the cars affected. It's not the same with the same 2 researchers. Not long after that, 2 years later, they published another case. It's on the same car. This time, it was required that they need to physically connect their attack device to the car network of the car. This allows them to target an ECU that sends command to the vehicle. This ECU is put into a booting loop and allows them to send malicious control commands directly from the attack device. The things they can do now is much more than before. So they can stop the car, speed it up, look or prevent driver from using the steering wheel, which is not possible before, obviously. So it's a very dangerous thing. So we want to prevent this thing from happening, and one solution, which is a common approach to deal with cyber attack on CAN bus networks, is to develop intrusion detection system, IDS, by which the machine learning can be used to differentiate between normal traffic patterns on the bus. This allows the IDS to alarm when abnormal or malicious traffic occurs on the CAN bus network. The normal step in this approach include, first, we collecting the data from a real car via the OBD port. Then the data may be pre-processed suitably to concentrate on relevant messages and features. Then training can be done via applying suitable machine learning models such as one-class support vector machine, recurrent network, or deep learning, and so on. In our group, one of our PhD students has developed an one-class support vector machine model for such an IDS. The trained model then can be evaluated usually by using offline data that has been collected, and then apply standard machine learning techniques such as cross-validation. The problem with this approach is that the data is usually limited. They don't represent a rich set of driving scenarios, and furthermore, live testing of the model is never used. And let us quickly describe, explain why that's the case. There are many obstacles to carry out for performing live evaluation of such IDS. Mainly, any attack on a vehicle can put the vehicle not suitable for running on public roads, such as well as there would be concern on safety of the driver. Even if we ignore these two things, then live testing must be done on private test track, which eventually leads to the restriction of driving scenarios. To overcome this problem, the common approach, a common solution, is to test them on suitable testbed. However, by doing a comprehensive review of existing testbed, we cannot find a suitable one that can help us. Let me give you 3 examples of such testbed. So one of the early one, for us, it's not actually qualified as a testbed, but they name it anyway. So this one called Octane, which stands for Open Car Testbed and Network Experiments. This is software-based testbed. On the top layer, the testbed provides a graphical interface to control and to monitor in-vehicle networks. This means that messages can be sent and received through the, so you can see here from the bus control where you can send messages, go all the way to the in-vehicle network, or you can receive and monitor the traffic on the vehicle network here. The way they implement that, they have a separated graphical user interface and a separated layer for send and receive, which is about programming really, and they put it in different threads so that they can be performed concurrently. They also have a hardware abstract layer where they would try to hide the detail of any hardware specific and then only focusing on type in-vehicle network, like you can see here, the CAN or FlexRay, and then they would defining suitable API to use each of these interface, each type of networks. And then depend on different hardware that can be used, they provide the interface between the abstract and the hardware API level. So if they use a conveyor devices, then they're gonna have to translate the API of the devices into the API of the corresponding network on the abstract layer, and so on for other devices like CAN, AVR. And the way they do this is that they want to aim for budgets, hardware, so you don't have to spend a lot of money on this. And then finally, it would connect it to the real devices. And so when we look at this one, it look like only a set of softwares really to allow you to control, maybe to inject the message or to monitor the buses. And it would not be suitable for, actually to have to developing any intrusion detection system, for example, and or to validating them. And especially there is no, it doesn't provide any driving scenario. The second more interesting testbed is actually come from Miller and Valencia, where they developed this testbed called mobile testing platform. This is a hardware-based testbed, which is assembled from real ECUs, from real CAN bus network, and from real, automotive components. And they put everything on a kind of racing go-kart. From what we can view, and this one is actually a miniature of a vehicle, which limited itself to the development and validation of IDS due to, very similar concern we have with actual cars. So it's a nice thing to have, but obviously, if you want to do it, then it maybe very limited in a limited ways. And finally, we look at a more recent testbed called PASTA, which stands for Portable Automotive Security Testbed with Adaptability. The testbed contains ECUs realized by general purpose microprocessors, which help to generate suitable CAN bus traffic on real physical bus. The testbed features simulation inputs such as steering, gas pedal, brake pedal, and so on. However, this is rather simulated and not suitable for generating different driving scenarios. So you can imagine that, you only to control this steering wheel or the brake pedal and the accelerator pedal and light, but come to when you want to see, realistic traffic, then it would not be easy, it would not easy to do so. And it would be not easy to argue as well. So in the end, we come up with a set of minimal requirement that we would like to have for a testbed to be. This one contains 4 requirements. The first requirement is about providing realistic scenarios. So it's the R2. The second is to replicate in-vehicle the ability to replicate vehicle networks on an industrial graded level. The third one is the must for support hardware plug and play so that we can add real ECUs and or attack devices. And finally, the testbed must be able to have the development and validation of security solution for in-vehicle networks. So based on these requirements, we come up with a logical device, a testbed that we would like to have. So in our design, we identify components of the testbed that we must have to fulfill this requirement. For requirement number 1, which is about realistic driving scenario, then we using a car simulator to provide different driving scenarios. For requirement R2, then we would need a an in-vehicle network simulator that commonly used in automotive industry. To satisfy R3 and R4, we must also have physical part of the network from the network simulator so that physical ECUs can be attacked and operated within the testbed. And finally, there would be a data storage to collecting data for training as well for validation. Then from this design, our next step is to implement the testbed. The first component is relied by a car simulator, CALA. So this is an open source simulator that is used to evaluate driving algorithms for autonomous vehicles. They are highly customizable to generate different driving scenarios based on different maps, vehicles, weathers, and so on. The network simulator is relied by the software Canoe running on a hardware simulator VN7814 by Vector. This is an industrial-grade simulator that is commonly used in the automotive industry. They also provide physical interface to physical canvas. This allows physical ECUs to be connected to the testbed. For example, we connected an instrument cluster here. You can see that we actually connected an instrument cluster to the testbed and also an attacking device. So this one is a mileage corrector, which can be easily obtained from eBay. And we also have an OBD port in the testbed so that as a suitable devices can be directly connected to the testbed. And well, in fact, the instrument cluster is not connected directly to the physical bus, but through the attack device. This allows us to demonstrate the effect of mileage tampering attacks in the testbed. This is the picture of the actual testbed that we have. The laptop that you can see here is actually running CALA simulator. The white box here is a canvas simulator that running Canoe. They also connected via, so these two connected via Ethernet via a network router. The physical bus, so you can see here the physical bus is a canvas physical one, which features an OBD port here. We also connected the attack device, the mileage corrector, and then the canvas, the green line here connected to the instrument cluster. The mileage correctors operate in 4 modes. In mode 1, it is inactivated. In mode 2, it reduces the mileage increment speed by 10%. So this means that if you drive your car in 10 miles, then it only records 9 miles. In mode 3, this rate is reduced to 50%, and in mode 4, it is 100%. So this means that your instrument cluster would not record any increment in the mileage. Okay, so now let me go to the first example that we show how we use this testbed. In the first example, one of our PhD students uses to develop and test his IDS implementation. So we collect the data directly from the testbed. Suitable data processing has happened here, and then would provide the data set for training with the one class support vector machine, and then the final step in which we done here is to do an offline validation. So this means that we actually get the data and to measure how effective the model is. So this is the result that we obtained. So you can see that for different mode we collected the prediction from the model, and we record how many times it's decided that the mileage corrector is active, and how many times it decides the mileage corrector is inactive. And then we did that for each mode. In the end, we measure then the precision is about 97%. So it's quite nice. But then when we deploy the model into the test bed, so the model now is put on the Raspberry Pi. The Raspberry Pi is now extended with a CAN hub that provide interface to the CAN bus network, and now it connected to the CAN bus through the mileage corrector. And then we run the test again, and this time we record the same things, and the precision score is actually now reduced to only 76.8%. What it means is that it shows that the training model must be improved, because it has too many false negative in some sense, and we need to have to collect more data to train it with more driving scenarios. And so we can see that this is the how say the effective the benefit of having the testbed. So another example of our testbed in action is to test a security solution from Siemens in our joint project called Secuka. This project is funded by Innovate UK. They propose to use our testbed to validate their solution IPs so that they can provide more proven evidence to their customer. In their solution, SoC is embedded with monitors within the SoC to collect the data that flow between the component of the SoC. And then any malicious behavior can be detected via suitable analysis on top of this collected data. And they propose 4 cybersecurity use cases. So the first one is a mileage tampering, where the attack aims to violate the integrity of the mileage counter. The second use case is about the attack that target the CAN bus via the OBD port. The third one is about unauthorized access happen to the memory of an infotainment unit. And finally, the last use case is about the unauthorized control of the door lock. To realize these use cases, Siemens implemented their IPs in an FPGA, where on top of that, they emulate the 3 relevant ECUs, so instrument cluster for use case number 1 and number 2, which is the mileage tampering and the OBD port, and the door lock ECU for the door lock attacks, and it's very simple infotainment ECU for the infotainment memory attacks. So the FPGA is also configured to provide a CAN interface so that it can be connected to the testbed via the physical CAN bus. So this is the CAN interface that it actually has. To realize the mileage tampering attack, we connected the FPGA via the mileage corrector. The OBD attack is realized via the OBD dongles. Finally, the memory attacks and the door lock attack are realized via a virtual terminal of the FPGA. So I would like to demonstrate these 4 use cases, but but with the help from my colleague Hesam, so he is kind enough to help me to record the video. So let me try to play this. So I just wondering about the sound coming out of this video. So let me try.
I demonstrate 4 abuse cases of secure CAD project. The first one is the mileage tampering, which is realized using a CAN filter. In order to activate the CAN filter, we need to turn on and off the high beam for 8 times. As you can see, the first mode of CAN filter is being detected by the Siemens solution, and at the same time is being corrected and displayed on the virtual dashboard. The second use case is the OBD tampering, which is realized using a Wi-Fi OBD dongle. We can use a third-party app which connects to the dongle. The connection is being detected by the Siemens solution. Also, collecting data through the OBD dongle from the physical CAN bus is also being detected by the Siemens solution. The other accumulated inside the FPGA can be demonstrated by sending an unauthorized access through the Python session to the CAN bus. The first one is the containment attack access, as you can see by sending the request. Siemens solution can detect the intrusion, detect it, and then fix it. The second one is the door lock, which you can also see by sending the unauthorized access. The door lock emulated ECU, the Siemens solution can detect and mitigate the abuse case.
Okay, so I think I'm not sure. Maybe the quality of the video is tricky through online session like this, but I hope that you can get the ideas from that. But any question? That also conclude my presentation. So any question, please?
Thank you. It's really an impressive work. So I have a quick question. How much does it cost to build this test bed?
I think it's about 30K.
Ah, okay,
Yeah.
right. So does that include the car simulator or not?
Yes.
Okay, okay.
So the car simulator is the open source one, so it's the cheapest one in the test bed.
Okay.
The expensive one is the FPGA and the vector box, the white box that you can see.
All right. Okay. Right. So let's see whether we have questions from the audience. Anyone, if you want to ask a question, you just you can ask directly, or you can paste your question into the chat. Okay, so let me ask another question then. For evaluating these test beds, what are the main criteria we can use? For example, we know there are some functional requirements. I guess it's already being met by this test bed. But other than that, are there any other performance or accuracy or any other criteria that can be used to evaluate this test bed?
Yeah, I think this is a good question. So this is something that we also consider when we implement the testbed. So one of the things that we really want to mimic, let's say that way, is to make sure that the testbed represents some kind of realistic traffic from rear vehicles. So in our project, then we actually we have from other partner, we actually obtain real traffic, canvas traffic from a rear vehicle. So I'm not allowed to say, but based on that, we replicate in terms of all the canvas, the message, the ID of the message, the frequency of the message, and also the timestamp of the message. So when we generate the data on the traffic, then it look almost exactly the same. There are still messages, some of the messages that we don't understand, and we don't put it there, but any message that we understand, then we put it there. And as I mentioned, we also have a rear instrument cluster from the same vehicle, then we also put it there, and then it works as you can see from the normal cars. So that is one thing that we really want to have, and it worked out quite well.
Right.
Yeah.
Okay. So Luca, do you want to ask the question yourself?
Yeah, thanks for the talk. It was very interesting. I was wondering if you had shared the data set anywhere so we can experiment with it somehow.
Yeah, we haven't, but we would love to share at the moment. So if you want, then you can contact me, and then we can arrange that. I already shared with some of our research partners, not in the project, but outside the project, but we want to do something else, then we also open to share. So that's not a problem.
Perfect. Then you might hear from me in your email soon.
Thank you.
Okay, so next question, Sampas, do you want to ask a question yourself?
Yes. Usually, how many ECUs can be connected to this testbed? We know that in a real vehicle there are like around 100 ECUs are available, but in this testbed, how many ECUs can be connected at one time?
It's a tricky question for me. We don't have many ECUs to connect it to be frank. But one of the reasons that we actually use industrial graded in-vehicle simulator here, so it has been used in the industry, so we expect it should be the same. So we can connect it to any number of ECUs that you can provide, that we have. And I think it also depends on the development model that you have, right? Sometimes in our model, we actually have some of the ECU virtually inside the box, and anything that we want physical, then it is outside the box. But from my point of view, then it can connect it to any number of ECUs. Yeah.
Right. Any other questions? So from your introduction, actually, the security is quite bad in cars. Have the car companies started to do something to replace this CAN bus network?
I think that's a very interesting point. So at the moment, CAN bus is still widely used, and almost every car coming out is still use CAN bus. And currently there are new type network that is promoted to replace CAN bus for many reasons. I think one of the reasons is about security. Another reason is also about the speed of the network. So CAN bus has been around for 20-30 years, so the speed nowadays is probably it reached its limit. And so I think examples like one of the promising one would be automotive Ethernet. I think that's one thing that people really want to do now. So it speed is faster, it's more secure, and that could be the solution, one of the solutions.
Right. But if they need, for example, authentication, then for each ECU, it needs to have some sort of security chip to store a secret key or public key, something for authentication then.
Yes. Yes.
And I guess one thing is really how fast they can compute, for example, for each message they send, like signature or other things. Because
yes, I think you're absolutely right here. So this is the trade-off, right? Whenever you're talking about cybersecurity, you need to consider trade-off. So it's about, so customer want cheap product and then also one secure product, then you may have to meet in the middle, right?
Yeah, that's true. That's true. Yeah, but the more electronic chips controlling the car are used, I guess it's more insecure. The car is.
It's difficult to say in that way, right? So so we are surrounded by, let's say, computer nowadays, not only in cars, in home, everywhere. And it's all about how to ensure that your desired product to be secure. And the more open your system is, the higher chances that you're going to be attacked by someone, right? So it's more all about, to ensure. I think this is why security standards is very important. So when you're selling a product, I think, now new standards has come out for automotive. So you need to make sure your product is, let's say your product meets standard, maybe at the minimum level, maybe at the, when you willing to pay higher cost, then you can have more features in terms of cybersecurity.
Right. Yes, that is true. That is true. So sometimes, do you want to ask the second question?
My question is, apart from the changes to the data due to the attack, we know that the attack will change the CAN ID sequences, so the payload of the CAN frame. But apart from that, is there any possibility to monitor other changes due to the attack, like voltage changes of the ECUs or any other kind of changes apart from the data itself?
This is something that is not my area, so I cannot say for definitely, but I think yes, it's, as long as you provide some kind of data, some kind of signals, then depend on your approaches. If you choose an approach to, for example, like differentiate between the normal behavior of the voltage, for example, then you can definitely detect any abnormal from this normal pattern. How well you can be, that's another question, right? It's about how you can train the data, how you can collect the data. If you want to look for some kind of simple rule-based mechanisms, then it may be different. I think it can be a simple solution, but it may not be true in general, I guess so. Is that satisfied with you? Or?
Yes. Thank you.
Okay, thank you.
Okay. So let's see. Do we have other questions? So another question is actually about not about the testbed itself. It's about the IDS system. So when you use the IDS system, what can you do if you detect an intrusion? And the second thing is, what if you get false positive? Then what can we do?
I think we don't want false negative, right? So what you don't want to scare people, especially I think that is in terms of reputation, that is very negative. So for the first question about when they detected some malicious behavior, activity happening, then what should we do? I think it's the same as now you have any car that you have a dashboard. Whenever something wrong with the car, you're gonna have a light somewhere turn on, and usually so I think that there may be different level of different level of reaction that you can have. For example, if it's a red light showing somewhere on your dashboard, the common practice is to stop not using your car.
Okay.
Yeah. If it's yellow one, you can use this for a little while, but probably to drive it to a garage to have a check. I think so. So it depends on the severities of the detections, and for car users, they don't want to have a very complicated message. So that's how the way that they design the car so far. You know, if when they driving, you give a long message, no one gonna be able to read it. You know, it just need to see the light, the kind of indicator to say, and then some common rules to follow. So that's what I can think of so far. Yeah.
Yeah. So the usual way we use IDS in network, for example, is we don't do anything. We don't react immediately to the alarm. It's being logged, and then someone will take a look into it, and then find if there is really an intrusion, then they will react on that. But is that enough in terms of a car? Because if someone trying to stop your car while you are driving, you detect it and then you display something, but the user may not have time to really look at it, and maybe the accident just happen at the same time.
Yes. So that's why I said it's about the severity of the detection, right? So if it's yellow, similar to the situation you described, so maybe now driving to a garage and someone gonna look at that, maybe look at the data to see what's happening here. But if it's a red one, it's like affects the safety of the cars, then the only way that you probably have to stop immediately and and maybe tow your car to a garage instead of driving yourself.
Right. Yeah, I guess it's a tricky question. It's a tricky question. What to do? Yeah.